Okay, so what we're going to do now is we're going to find the period for oscillation for this system. Okay, so the masses are oscillating back and forth, and we're going to calculate or come up with an expression that gives us the time it takes for one cycle. Okay, so now we're going to find the period for our simple harmonic oscillator. So we abbreviate SHO as simple harmonic oscillator. Okay, so the idea is I have a mass on a spring, okay, so it's in simple harmonic motion. The mass and spring system is a simple harmonic oscillator. Okay, so I have the mass, I have the spring constant. Okay, so I want to find the time it takes for one cycle. So let's say I let it go here at the amplitude, and it's going to go, and I want to find that period t. Okay, so we're going to go back to Newton's second law. Okay, so I'm going to apply F equal ma to the block in the x direction. Okay, so yeah, I mean, I know there's the normal force, and you have an mg. Okay, those are in the y direction. Okay, so I don't need to draw those forces. So the only force we're worried about is the spring force. Now, I'm not going to draw the spring force because depending on where the block is, right, when the block's on the right side, spring force points in that direction. When the block is on the left side, spring force points in that direction. Okay, so I'm just going to write down Newton's second law, and I know that the spring force, the Hooke's law spring force, is minus kx. Okay, so my spring force is minus kx, and that's equal to ma. So we just went through the analysis where we had our position as a function of time, and we found the velocity as a function of time, and we found the acceleration as a function of time. So for the position, I'm going to put in what x is, okay? And for the acceleration, I'm going to put in our last result, what the acceleration was. Okay, remember the acceleration was minus a max cosine, where a max was x max omega squared. Okay, so I put that right there. Okay, now my amplitude cancels, my cosines cancel, my minus signs cancel, okay, and all I'm left with is I have a k, and I have an m and an omega squared. Okay, so I solve this for omega. Okay, take the square root of both sides. All right, so that gives me what omega is. K is the spring constant, m is the mass of the block. All right, but we know that omega is 2 pi over the period. Okay, so the period is then 2 pi over omega. So the period is 2 pi over that whole thing. Okay, so right here I have omega. I'm going to put in square root of k over m, and that's what I did right there. Okay, and remember, this is in the denominator, so the m flips up on top, and that gets me the period. Okay, now the good thing about these chapters is if you know the period, you instantly know the frequency because the frequency is just 1 over the period. Okay, so I invert the period, and that gives me the frequency. Okay, so if I take a mass and a spring off the shelf and I oscillate them back and forth, okay, or I should say I can oscillate them up and down, okay, it only depends on the mass of the block and the spring constant. Okay, so this is an interesting result right here. Okay, so here's a property of simple harmonic motion that both the period, there's a period, and the frequency are independent of some variable, okay, that you would expect to kind of be in these equations. So if you look at what we have up here in this picture, okay, and then you go down to these expressions we just found, okay, you ask, well, there's another variable up here that you would think would affect the period, okay, and the frequency that doesn't show up, okay, and that's the amplitude, okay. So it doesn't matter if you pull it back to here or pull it back to there or there, okay. The amplitude, there is no amplitude in the square root. So if you have a system, okay, and you pull it back a certain distance and let it go, and it goes back and forth, back and forth, back and forth, okay, and then you pull it back maybe twice as far, okay, and you let it go, and it goes back and forth, back and forth, back and forth, okay, and you find the period's the same, then you have reason to believe you have a simple harmonic oscillator. So the period and frequency are independent of the amplitude, okay, And that's not obvious that that would be the case, but I'll show you a video that actually demonstrates that we have a mass in a spring. You pull it down a little bit and it oscillates back and forth, okay, very slowly. But you pull it back a lot and it oscillates rapidly, okay, meaning I should say the velocity or the speed is fast because it has to cover a big distance in that same amount of time that this one had to cover that short distance. Okay, so that's a really weird result, that the period and the frequency don't depend on how far it's stretched. All right, and actually in the lab we're doing now, if you look at the data, you have the mass, you have the spring constant, but nowhere in the lab did we need to know how far this thing was pulled down and released.
1, 2, 3, 10. 1, 2, 8, 9, 10.